These are notes over a type 1 example. So type 1 is, just as a reminder, a flat ground over flat ground. Okay, so for the problem, a soccer player kicks the ball on a level playing field with an initial velocity of 11.3 meters per second at an angle of 35 degrees above the horizontal. Find the time of the flight, the range, the maximum height, and the final velocity of the soccer ball. Okay, so the first strategy in order to solve this is to draw a diagram. I would suggest that you always draw a diagram just so that you know exactly what you're trying to find. Okay. And then I already went ahead and drew my diagram, and I labeled my initial velocity, okay, which is the purple arrow, 11.3 meters per second, at 35 degrees above the horizontal, so I put that angle in there as well. And then I went ahead and completed the right triangle so that I have the X, and then I have the initial horizontal or vertical Vy, V1y velocity. Okay, and then also I define the positive directions as up and to the right. Okay, so the next step that we're going to do is we're going to solve for Vx and Vy. Okay, so to solve for Vx and Vy, we're going to use the cosine and sine. So let me get my pen. So first we'll start with Vx. So Vx is adjacent to the angle of 35 degrees, so we're going to use cosine. So cosine of our angle, 35 degrees, equals Vx over 11.3. Okay, so we're going to times both sides by 11.3. Okay, and we will get that Vx is 9.26 meters per second. Okay, and then for V1y, it's the opposite of the angle, so we're going to use sine. So sine of 35 degrees equals V1y all over the hypotenuse, which is 11.3. So times both sides by 11.3. Okay, and we'll get that V1y equals 6.48 meters per second. Okay, so we solved for Vx and V1y. All right, the next thing is to write out the horizontal and vertical variables in separate columns. So I'm going to keep it the way I have it currently. So I'm going to have the horizontal here, and then the vertical. Okay, so for the horizontal, we're only going to have 3 variables, and so if you look at your last page of your notes, we kind of defined what 3 variables we're going to have, so I'm just going to go ahead and write them. So we're going to have displacement in the x-axis, we're going to have the velocity in the x-axis, and then the time elapsed. All right, and then for vertical, we're going to have displacement in the y-axis. We're going to have the initial velocity, the final velocity, acceleration due to gravity, and time. All right, so now we can go through and define what we know. So we do know that the velocity for x is 9.26, because that's what we just calculated, meters per second. Okay, but that's the only thing that we know as of right now as far as the horizontal. For the vertical, we just calculated the V1y, the initial velocity, as 6.48 meters per second. Okay, we also know acceleration is negative 9.8 meters per second squared. Okay, We also know the displacement of y, okay, because if we start here and we end here, okay, our vertical displacement is going to be 0. Okay. Now, because we only have one variable for horizontal, we have at least 3 for the vertical, we can go ahead and solve for one of the variables in the vertical aspect, okay? So we can use equation 3. And so if you look back at your notes from the kinematic equations, you can look, if you have at least these 3, what variable can you solve for? Okay, so we're going to go ahead and solve for time. Okay, so equation 3 is the displacement of y equals v1 delta t plus 1/2 acceleration change in time squared. Okay, so our delta dy is 0 equals our vy1 is 6.48 times t plus 1/2 negative 9.8 t squared. Okay, so we are actually going to have to factor this because we do have a squared. So first let me kind of simplify. So we have 0 equals 6.48 t minus 4.9 t squared. Okay, so factoring this, I can pull out a t. So I would have t 6.48 minus 4.9 t, and these are equal to 0, and then so I can set the 2 different factors equal to 0. So the first one is 0 equals t, and then 0 equals 6.48 minus 4.9 t, and then solve for t here. So I'll get negative 6.48 divided by negative 4.9 equals t. So I'll get that t is 1.32 seconds. Okay, so the reason that we have 2 answers here for time is because this is the start time and this is the end time. Okay, so now we have time. So time, I'll go ahead and put the total duration is 1.32. Okay, and so we actually have, because time is a scalar, it's going to be the same for both. So 1.32 seconds on this one as well. So now we can go ahead and find the range, which is the displacement in the x-axis. Okay, and real quick, just so that we are kind of staying organized, we have the time of flight. I'm going to just kind of highlight as we go along. Okay, so the next thing we're going to do is range. Since we found time, now we have 2 of the 3 variables in the horizontal. So we can go ahead and solve for that. Okay, so for the range, we're going to use delta, or the velocity equals distance over time, or displacement over time. Okay, so if I plug in what I know, we have 9.26 equals dx over delta t, which is 1.32, which is what we just found. Okay, so times both sides by 1.32, and we'll get that delta d x equals 12.25 meters. Okay, so 12.25 meters. Let me go ahead and mark that one. So our range is here. For the next part, we're going to move on to the maximum height. To find maximum height, there's two ways that we can actually solve for this. Okay, so we can either set that our final velocity for the vertical aspect is at 0, okay, because at the highest point here, okay, the final velocity, if we were just trying to find the maximum height, would be 0, okay, or what we can do is take the time and divide it by 2, because we know since the parabola is symmetrical, we can just cut it in half, basically, the time, in order to find the point in which it's at its max height. Okay, so either way would work. I'm going to go ahead and use the half of time. Okay, so if I have our time, which is 1.32 seconds, divided by 2, I'm going to get, it's at time of 6.66 seconds. So that's when max height occurs. Okay, so then I have to plug it in back into that kinematic equation, the equation number 3, to find the height. Okay, so delta d of y, this is for the max height, because it's only at the halfway point, is equal to the initial velocity, delta t, plus 1/2 acceleration times delta t squared. Okay, so plugging in what we know that our initial velocity in the y direction is 6.48 meters per second. Oh, I'm going to actually leave that out for the equation. Times our time, which is 0.66, plus 1/2 times our acceleration, negative 9.8, times time, which is 0.66 squared. Okay, and so if we multiply this all out, we're going to get that delta d of y for the maximum height is going to be 2.14 meters. Okay, so this is the maximum height. Okay, and like I said, you could have just set V2 to be equal to 0, and you could have used a different equation, one of the different kinematic equations. So our maximum height is green. The final thing we need to find is the final velocity. So once the object actually hits the ground. Okay, so we could actually go through and calculate everything, but if you remember back to our notes, and real quick, I did forget to put a negative here in for this. We know that if we have a flat surface and our parabola is symmetrical, that our final velocity is going to equal our initial velocity just in the negative direction. Okay, so they're going to be equal but opposite. So equal in magnitude but opposite in direction. So since our initial velocity was 11.3 meters per second, 35 degrees above the horizontal, our final velocity, so V2, is going to equal 11.3 meters per second, and it's going to be 35 degrees, and it's going to be below the horizontal. So BTH stands for below the horizontal. Okay, so that's an easy way to remember or to solve for it because we know that it's over a flat surface. Okay, so that is our last part that we had to solve for.